You look up into the sky and see an aircraft flying toward you at Mach speed. Everything is silent as the plane approaches. You expected to be able to hear the roar of the engines as it got closer, but it's not the case. You look through a pair of binoculars at the object and can see the flames from the jets coming out of the back, yet there's still no sound. When you glance down at the trees below the plane, it seems as if some unseen force is bending them. The supersonic jet passes over you. There's a sudden increase of pressure and a deafening boom. You just experienced a sonic boom from the aircraft that flew over you. Mach 1 means that an object is traveling at the speed of sound. Anything over Mach 1 means an object is going faster than the speed of sound and will create a sonic boom. The loudness and intensity of the phenomenon is determined by several factors. But what is a sonic boom? A good way to think about the concept of sonic booms is to imagine that air is a fluid. When a boat travels through waters, it creates ripples that radiates outward from the front of the boat. The same thing happens with a plane in the air. As an aircraft travels through the air, the sound waves it generates radiate out in a similar way to ripples in water from a moving boat. However, when an aircraft goes supersonic or exceeds the speed of sound, it means the plane is moving faster than the sound waves it's creating. This is why an aircraft that's approaching you at Mach speeds appears to be silent until it passes over you. This phenomenon results in a sudden change of pressure between the front and the tail of the aircraft, which results in a shock wave, or what we call a sonic boom. But a sonic boom is not just generated at a single point, it's actually a cone shape called the Mach cone. Anyone within the area of the Mach cone will experience the sonic boom of an aircraft going faster than the speed of sound. So the plane does not need to fly directly above you. The sonic boom is not the noise of the jet engines or the object itself. It's actually the sharp release of pressure that occurs between the built-up shock wave in front of the aircraft that collapses into the space the aircraft previously occupied as it moves through the air. An easier way to think of it is that due to the natural forces of physics, this incredibly high pressure that builds up in front of the plane wants to fill in the space that the aircraft occupies. A simplified example of this can be seen when you wave your hand back and forth. You can feel the air move over your hand. This is because as your hand moves, the air molecules around it flow over your hand to fill the empty space that your hand once occupied. This all has to do with changes in pressure. The space where your hand was has a lower concentration of air molecules than the surrounding area. This causes the molecules to flow toward the area of low concentration in order to equalize the pressure. If you could move your hand at 761 miles per hour, you could create a mini sonic boom as your hand moved through the air. The same thing applies when an aircraft reaches supersonic speeds. The buildup of pressure at the front of the plane instantly fills the space behind the tail of the plane, where the aircraft was a moment before. This is what causes the sonic boom. The size and distance of the sonic boom created by the Mach cone is influenced by several factors. Things like weight, size, and shape of the aircraft all impact the sonic boom's intensity. Also, the speed, altitude, and flight path that the aircraft takes will affect the Mach cone. A large, heavy aircraft will displace a lot more air than a thin, small aircraft. This means that the larger aircraft's sonic boom will be much stronger and louder. The more air displaced by an object going supersonic speeds, the bigger and stronger the sonic boom will be when the pressure change occurs. Altitude also plays an important factor in how intense a sonic boom is. The higher a supersonic aircraft is flying, the wider the area of the Mach cone will be. This is because the shockwave needs to travel a further distance to reach the surface of the Earth than a low-flying object. However, altitude also influences the speed at which sound moves. At sea level, the speed of sound is around 761 miles per hour. This means that any object that travels faster than that speed will break the sound barrier. The area within the Mach cone where the sonic boom can be heard is called the boom carpet. Researchers can calculate the exact dimensions of the boom carpet to know how much area will be affected by the sonic boom of an aircraft flying overhead. The width of the boom carpet is about 1 mile for every 1,000 feet of altitude. This means that if a supersonic jet is flying 60,000 feet, its boom carpet will be about 60 miles in width. That being said, not all points within the boom carpet will experience the same intensity of shock waves. The spot directly beneath the aircraft will have the highest intensity and experience the most powerful sonic boom. The further away someone is from the flight line of the aircraft, the less intense the boom will be. Any object traveling faster than the speed of sound actually generates 2 sonic booms. This is because there are 2 changes in pressure as an object travels quickly through the air. The first is at the front of the plane, where a huge amount of pressure builds up around the nose. The second is at the tail of the aircraft, where the pressure suddenly returns to normal. The 2 sonic booms are normally about the same strength. The time between the two is dependent only on how large the aircraft is. The longer and bulkier a plane is, the more time there will be between the 2 sonic booms. Conversely, if an aircraft is small and thin, the time between the two sonic booms will be so short it might seem like there's just a single shockwave. However, this is just an illusion, as every aircraft going over Mach 1 creates two sonic booms. A good example of this phenomenon occurred when NASA used to utilize space shuttles for their missions. During re-entry, the shuttles would be traveling much faster than the speed of sound. Since these crafts were so large, the time between the two sonic booms was very noticeable. Interestingly, speed doesn't have as much of an effect on the intensity of a sonic boom as you might think. The faster an aircraft goes over Mach 1 does not necessarily correlate to a bigger sonic boom. At speeds slightly faster than Mach 1, like Mach 1.3, there's a significant increase in the power of the sonic boom. However, at speeds faster than Mach 1.3, the change in the intensity of a sonic boom is negligible.